to congratulate the organizer. I'm not thanking you because you didn't invite me, but in any case, I'm congratulating you for the organization of this conference. I think it's a very good addition to the kind of many conferences on quantum-related stuff that we have in Brazil. So live long to quantum at the dunes. So my talk today here is somewhat very related to the talks by Jens Isaac, Tony, and of course Thiagos, in the sense that I'm interested in knowing how the impact of somehow a ontological lack of precision, how does that impact your description on quantum mechanics? Okay, but before I go there, so yeah, there's this jet lag thing. So I didn't know I would speak just after Thiago. So okay, so that's the other direction, so to say. So I mean, just want to show you where I work. It's not on the top of the mountain. It's actually just a little bit behind. So this picture was taken from this cable car that goes to the Sugarloaf. So it's a very nice place. I mean, you have physics. So it's a Brazilian Center for Physics Research. So it's one of the very few research centers in Brazil, like IIP, I'd say, right? But we do have like research in many areas, and recently we've been pushing a lot the quantum technologies thing, and so we have experiments on quantum sensors, quantum computation, and the one that I'm most connected to is the Rio Quantum Network, which is it's a network, it's a metropolitan network connecting many research institutions in Rio de Janeiro, and now we are maybe extending it to São Paulo. And this is done by people, of course, and I'm very happy. You can clearly see an age gap from the first line to the second line, and all these people here have just been hired, so we doubled in size and more than doubled in momentum, so I'm very happy to have all of them now there with us at CBPF. Yeah, so and the theory is very small, as usual, right? So I mean, it's the permanent people are those here, and I put also Alfredo, who is retired, but he's like our mentor, and many of you know. So these are the students, and I should say that Mario is here. Where's Mario? There he is. He's working on the Rio Quantum Network, and today is his birthday, so congratulations, Mario. That's yeah. Yeah, he's going to be here. All right, so but the work that I'll be presenting today, as Thiago has just mentioned, was done by this sort of people, by this set of people, sort of people as well, set of people. So Gabriel and Pedro, they were PhD students in the group there, and now they are professors in universities. Paola was a postdoc at the time. Thiago is here, and Raul is my long-term collaborator back there in CBPF. Okay, so I need not convince you that quantum mechanics is one of the greatest achievements of humankind, right? But what started as a theory to describe the smallest part of energy and matter, like the hydrogen atom, I mean, we've been using to describe ever more complex systems like this chunk of metal, which has been put in superposition by the group in Vienna. So they saw this quantum interference with this metal ball with 7,000 atoms, right? So more and more we are using quantum mechanics to describe very complex things, and bringing closer to the subject of this conference. So we are all hoping for very, very complex quantum computers, right? So when I started my PhD, it was like 2-3 qubits, and now we're going thousands, and we have this promise by PsiQuantum of 1 million qubits this year, right? So it's 10 months to go, so I'm very curious how's this going to end. But okay. So what I like very much that this development on experiments is that, I mean, questions, yeah, I didn't start my time, so you have to take care of that. So questions which are fundamental from the very beginning of the theory. I mean, we've seen this picture already. Now they are kind of technological imperative that we must answer them, right? So that's what Thiago was saying, the transition from quantum to classical. And the main point that I'll be addressing here is this conundrum that we all know about it, which is, so if quantum mechanics is universal, so then it must apply to detectors, cats, human beings, right? And what this poses is then, so when should we use the unitary dynamics and when should we use the collapse dynamics, right? So that's the question that I'll be addressing, and what I want to see is what is the impact of finite resources on these type of questions. Okay, so that's the outline for the talk. So I'll just briefly tell you what Wigner friend scenario is about. Then I show the tools that I'll be using. Actually, Thiago already showed many of the tools that I'll be using, but I didn't know he would speak before me. But then the major part is this model of a measurement process using only finite resources. So that's the crucial part. And then I try to convince you that that sheds some lights on this Wigner friend problem. And then I draw some conclusions. Okay. Okay, Wigner friend scenario. So my pictures, like the pictures before that, they are also done by ChatGPT, right? So they get, so but they were better. I mean, they were worse in a sense, but they were more hallucinating before, so it's actually nicer, right? So Wigner friend scenario for me at least is just a dramatization of the measurement problem, okay? So this has been proposed by Wigner in 1961, but if you are interested, I suggest you to read actually this somewhat more recent article by Matt Leifer, I think that's how to pronounce it, group, where he has this nice review, and that's the one that I use the most, right? So, and the idea is more or less the following. So we have this experimenter here, and to her it was handed a experimental apparatus which has 3 levels. So it starts in the 0. I'm not sure you can see it, but there is a 0 here. I put in my hands because it's shaking. 0, so it can either go +1 or -1. Okay, and to her is also given a spin half particle which is prepared in a superposition of plus and minus, and what she has to do is to describe this measurement process. She doesn't even need to know quantum mechanics, but given that this has been calibrated, I mean, what she can say is that, what she can see actually is that with probability half, she'll get the +1 result, +1 outcome, and with probability half, she gets the -1. And when she gets the +1, she assigns to the system and apparatus the state +1. So minus, and then when she gets the outcome -1, she assigns to the system the state minus, and the apparatus the state -1. Okay, but Wigner has this Google Eye vision, and of course he does know a lot of quantum mechanics, and he might be willing to describe this whole thing unitarily, right? So then he gets to this entangled state, which is the superposition of +1 with -1. Okay, to this point there is no real contradiction. I mean, most interpretations of quantum mechanics do not have any problem with that. But what we can think, and this has been thought by Deutsch, that every time that she performs a measurement, a light goes on here, does not give any information about the outcome result, but just says an experiment has been performed. And what Wigner can do then is to perform a measurement on the system and apparatus, and even the friend if you want to, then he can measure this thing here. So these are the projectors that he can measure. So it's either phi plus or the orthogonal projector. Okay. So if this is the description of what's happening, then he's going to get with probability 1 the outcome related to phi plus. But if that's what's happening, then half the time he gets phi plus, and half of the time he gets projection on the orthogonal subspace. So then you see that there is a different probability assignments for the same experiment, and that's the issue, right? So that's what we are trying to understand here. But you must realize that there is a great assumption here, which is one needs to perform this measurement on the total system, spin plus apparatus, right? And so when reading these articles, then you see that at this point, people usually say things like, yeah, this can be done in principle, right? And that's what Jens Isaac was mentioning, that he was surprised that people do not take in account finite resources. I'm from Latin America. I mean, I don't get surprised. I get angry, right? And it's really, I mean, I don't understand how we still debating these things, right? I mean, how we do not take these things in account. And there is this very nice calculation by Peter Hyman, which was pointed out to me by Thiago, that he says this, I mean, he makes this calculation. So in a macroscopic system with 10 to 23 degrees of freedom, a small energy uncertainty of 10 to minus 10 to 22 joules still contains 10 to 23 energy levels. So these are mind-boggling numbers, right? I mean, there is no hope that we are ever going to such precisions, right? But okay, so there's a way to kind of somehow go around this, and the way is that, okay, so instead of making this measurement, what Wigner can do is actually he undoes the evolution, right? So he applies this U-dagger, so he gets back to, if he's using his descriptions, he gets back to the initial state, but in this description, so half of time you get back to +0, and the other half of time you get to ±. And now it's a simple measurement. I mean, you just have to measure the spin, right? And this has been done in many labs here. So just measure the spin in these bases here, and then you reach the same thing, right? So for him, every time he's going to measure, he's going to get the result related to plus, minus. And if you're using this description, half the time you get one, half the time you get the other. But then, of course, I mean, the main assumption again here is that, I mean, there's no free lunch, of course, and then the main assumption is that you can actually make the reverse, this perfect reverse of a measurement process, right? Which again, I mean, you see, well, this can be done in principle. But what I like this description is that reminds me of paradox that appear when we are talking about quantum, about statistical mechanics, and we do not take into account finite resources. So that's where we start to think about this. And so the goal here is to describe the measurement process with finite resources. And the way we're going to do this is using specific, to think the measurement process as an effective equilibration process, right? So by thinking this way, I mean, we are directly including finite resources. And I should point out that there is these people from Vienna that they are thinking the same lines of arguments, although the focus is a little different, but it's very related subject, very related results. Okay. So okay, so yeah, so that's the key message somehow. So if we manage to do this, so a measurement process will be for all practical purpose and thus in principle irreversible. Okay. So for me, there's a big difference when we say in principle in math and when we say in principle in physics. So these are completely different things. Okay, so just go quickly over the tools that we are going to use, because Thiago already introduced many of them. So we are going to say that an observable is in equilibrium if its expectation value at the given time t does not change, is not too different from the expectation value of this same observable in the equilibrium state. So what I'm trying to say is that if most of the times, I mean, this difference here is pretty much zero, then we are going to say it's in equilibrium. And the equilibrium state is just this convex sum over the evolution state in every time. Okay. So this is from Christian Gogolin's thesis. Okay. And so there is this nice result by Peter Hyman and some people. I mean, I think this existed before, right? But okay, I'm using this version by Peter Hyman. So if the Hamiltonian is non-degenerate with non-degenerate gaps, then what one can show is that most of the times, so the expectation value of the observable A does not differ from the expectation value of observable A in the equilibrium by more than this quantity here, which is the operator norm of the observable divided by the effective dimension, which is defined here, is somehow telling you how spread the initial state in the eigenbasis of the Hamiltonian. Okay, so if this here is small, then for you, most of the times you see the observable, it's equilibrated. And it's actually the same result, but I mean, just looking now for the state. So we want now to know whether the state at time t differs too much from the state, from the equilibrium state. And so what we're going to allow here is just for a set of available P of M's. So of course, if you can measure anything, then you can see the difference. But if you have a set M of P of M's with total number of outcomes that I'm calling M, then we can show this bound here. I mean, this is from Anthony Short article. So this distance will be small if this here is much smaller than the square root of the effective dimension. Okay, this was quicker, but I guess Thiago has already mentioned some of this. So these are just the tools that we are going to use. And now I go to the main topic of the talk, which is this finite resource model of a measurement process. And you can see it's sort of a toy model that we work with. Okay, so just the setup. So as before. So we have this one single qubit that starts in whatever superposition, but in a pure state. And to the apparatus, then we are going to assign a Hilbert space of d dimensions. And we are going to split it in 3 subspaces, the direct sum of 3 subspaces. The subspace connect to the +1 outcome, the subspace will connect with the 0 outcome, and the subspace with the -1 outcome. And the whole thing here is to make the subspace of the H0 subspace much smaller than the other subspace, in the sense that your apparatus starts here, and when it goes to either -1 or +1, then it stays there. Okay, but it has to be in this way here, because we want to be able to prepare the initial state of the apparatus. And actually, the initial state apparatus then will be this one here. I mean, the total state actually will be this. So it's the psi for the spin and the microcanonical state for the apparatus on the 0 subspace, because the only thing that we know is that it starts at position 0. So that's the initial state for our system, total system. So the Hamiltonian then is like the usual suspect. I mean, so if it's in the plus, see, if the qubit is in the plus state, so what we want is that this pointer here goes from 0 to +1, right? So then we have this Hamiltonian which connect these 2 subspaces and nothing on the other subspace. And if the qubit is in minus, then we want it to go from the 0 to the minus. So that's what we're doing here. But as I want to have these with finite resources, so all my results cannot depend on the fine details of these Hamiltonians. So what we are going to do is to sample these Hamiltonians from the GOE ensemble, and this has been defined by Jens Eisert in his talk. And by that we get many things. So we get directly that the gaps are non-degenerate, so there are no degenerate levels. And again, I mean, so this already sort of gives me that I don't need to know all the details of these Hamiltonians, and these will be clear with the results. Okay, so if I now use this result by Hyman that I've just shown you, using now the observables as the projectors that we measure, then what we can show is this, right? So the probability of having the outcome I, which it can be -1, 0, or +1 at time t, does not differ most of the times to the equilibrium probability measured on the equilibrium state. And this is smaller than something which is 1 over the sum of the dimensions. So if the dimensions are very large, so dimensions for the 0 subspace and dimension for the 1 subspace, which I actually said dimensions of the 1 subspace and dimension of the -1 subspace are equal, so then this goes to 0. So then you see that most of the times we get the probabilities that we expect. And moreover, as I said, this cannot depend on the Hamiltonians, the details of the Hamiltonians. Then if you pick this Hamiltonian at random from the GOE ensemble, what we show is that the difference between them, the probability for a given Hamiltonian at equilibrium to the average probability in the equilibrium, the probability for this to be bigger than delta is smaller than something that decays with the dimension as well. And the nice thing is that we can actually calculate these average probabilities, and these are the probabilities that we would expect from textbook quantum mechanics. So it's just the modulus square of the coefficients, C plus or C minus, times a factor which depends on the dimensions, right? So the whole argument is like this. For large apparatus, and most of the times we have this, so the probability of plus or -1 at a given time for a fixed Hamiltonian does not differ too much from the equilibrium Hamiltonian, from the equilibrium value for the probability, sorry. And this equilibrium value actually does not differ too much from the average equilibrium value, and the equilibrium value is this one here. And if the dimensions are large enough, then you get your textbook quantum, your textbook probabilities. And for the 0 subspace, this probability goes to 0. Okay, so we recover all the results that we would expect. And so that's how I'm doing on time, because I didn't. 5? Still have 10. Okay. Okay. So you cannot see it very well, but I mean, so here I just took 3 instances of Hamiltonians, like random Hamiltonians, for different set of dimensions. Okay. So the lines, they correspond to the equilibrium values, and these the full lines, correspond to the evolutions of the probabilities. And you see that if dimensions are small, so d naught is 2 and d1 is 7, then you see all these oscillations. But if you keep increasing these, so here is d naught 2 and d1 63, you see that all these lines, they converge. So all the results, they go to the equilibrium value, and all the equilibrium values, they converge to a single equilibrium value, which is the average equilibrium value. Okay, and that's the probability of having the outcome 0, which goes to 0. Okay. All right, so but that up to now I was talking only about probabilities, so maybe related to the question that Fernando was asking. So what about states, right? So I want to know how far actually I am from the equilibrium state. But again, so I do not have access to this Hamiltonian, right? So this actually cannot be known. So again, my results cannot depend on the Hamiltonian. So what we do, so we use it's the same line, the same chain of arguments. So first we show that, okay, so for a fixed Hamiltonian, most of the times we are not too far from the equilibrium state for this given Hamiltonian, and that's given by this, I mean, that's true whenever the dimensions are large, and they increase much faster, the dimensions increase much faster than the set of POVMs that you have. Right? And then given that, now what we show is that the equilibrium state for a fixed Hamiltonian does not differ too much from the equilibrium state from the average equilibrium state, sorry. Yeah. And this is kind of sort of Levy lemmas, and you see that it has a exponential decay. Right, so it's the same thing. And so here's just to show you how distributions kind of concentrate. So for small dimensions is somewhat broad. It's still very close to 0, the distance between the equilibrium state for a fixed Hamiltonian and the average equilibrium state. But then when dimensions increase, then they get concentrated, and they're very similar. And again, so the nice thing is that actually we can calculate this state analytically. The average state we can calculate analytically. And again, I mean, I always like to know what's the results before actually perform the calculations. And I mean, one can basically guess these results, right? So if you perform these averages, so what you get is that, well, with probabilities, which the probability that we had before, which is like C plus modulus square times a factor that depends on the dimension, then the state will be in the plus state, and the apparatus is going to be in the microcanonical in the plus subspace. And the same thing for the others, right? And the 0 is this one here, which has this, so, I mean, you have the mixture of the plus for the qubit with the minus, but it will be such that when the dimensions are large enough, this goes to 0. And I think that's what I have here. Yeah. So when the dimensions are large, sufficiently large, so then we approach to this limit here, which is again your quantum mechanics textbook result, right? So it's modulus C plus square times the state in the plus state, and the microcanonical for the apparatus in the plus subspace, and the minus C minus modulus square minus for the spin, and the apparatus in the minus subspace. And I mean, since that's the only thing that you know, so either plus or minus, that's what you should expect anyway. So, but that's what we calculate. And I should point out that these here, I mean, we didn't take any partial trace, nothing. We're just taking averages, right? So it's average over time and average over the Hamiltonians. Okay, so there are no partial traces here. So, I mean, these probabilities and these states sort of emerges from the construction. Okay, so another point which is important, of course, is the post-measurement state. But I mean, from this state that I've just shown you, it's very simple to realize what are the post-state after the measurement. So you just update your description. So if you were given outcome +1, then this is going to happen with this probability. Then you just say that's your state, and the same for the other ones. Right? And the important thing here is to realize that these states, they are not stationary, but they are going to be quasi-stationary. So in the limit of D1 much bigger than D0, if you start in the age 1 subspace, then you basically stay there, right? And for the D0, I mean, then you start the whole thing, the whole process again, but the probability that this is going to happen goes to 0 if d naught is much smaller than d1. Okay, so you see that you recover all your familiar results from textbook quantum mechanics. And going back to Wigner and his friend, I mean, so the way I see it, at least, so if Wigner is really describing a measurement, I mean, if he's willing to really describe a measurement, he wouldn't say it's a unitary description. He would have to average over all his ignorance, and that's what he would get to, and that's what his friend would say as well, so they would agree on the description. Okay. All right, so just to reach to some conclusion, so that's Wigner and Heisenberg, possibly a friend, possibly not. So just to conclude, so what we did was to introduce this quantum measurement model that accounts for finite precisions in microscopic systems, and we did this kind of consistently. So in the input state, in the dynamics, and also on the measurements. So the measurements are also kind of cross-grained, as Thiago was saying, in the sense that we are making these measuring these large projectors, right? So our model recovers the expected results for large apparatus in long time. So that's what I was showing to you. And so that's maybe a strong sentence, but so collapse dynamics sort of emerges as an effective description due to these limitations in describing the apparatus dynamics, right? So that's the point I was trying to make in the beginning. So if you believe that there is this sort of ontological lack of precision, so that's, I mean, the collapse dynamics can actually be derived from the unitary dynamics. And well, no contradiction is reached in the Wigner-Friend scenario. And that's it. Muito obrigado.
Thank you, Fernando. Questions? I can't do a question. Okay.
Yeah, that's not actually, because Thiago and I, we disagree a lot on this subject.
Thanks for the talk.
Thank you.
So maybe this is a silly question. I don't understand 100% the equilibration part. But if I understand correctly, so your answer to those proposed no-go theorems that say, for example, the local friendliness no-go theorem, if you violate this inequality, then there's this set of assumptions that's not. So your answer is that this inequality is never going to be violated because in real life we have finite resources. Is that right?
Yeah, I'd say yes, also. I mean, I would have to see the details, but yes. So that's something that we want to do afterwards, to extend to two friends and see all these theorems. But I mean, so I guess the point, so these graphs that I had there, so if you do actually have something that you can call a measurement happening, then I'd say these inequalities wouldn't be violated.
Okay.
But of course, whenever it's violated, then I can say that maybe it's not a measurement. Like the experiment that has been done, I would say, and I guess everyone agrees, it's even written in the article that it's not really a measurement which is being carried out.
Yeah, that was my follow-up question, like, because the theorem applies to whatever you want to call an observer, and then in that experiment, the observer is another qubit. So most people would not call that an observer, except for Carlo Rovelli, I guess.
Yeah.
And yeah, so then I was just gonna ask, like, for you then, what is an observer? Does it have to be a...
Yeah, I mean, I don't have a kind of a clear answer to that. In the sense, like, I mean, I don't see, at least not for the moment, like a kind of very specific border, right? So something that I would like to do is to maybe get a number for these ontological imprecision, but I don't know how to do this.
Okay.
So
then in your model, you have some parameter for the ontological imprecision, and then if you change this parameter, you kind of change the size of the large apparatus, something like this?
I mean, that's what we wanted to do at the beginning, but that's not what we managed to do. So what we did actually, I mean, what we wanted to do is to have this Hamiltonian here and having somehow like perturbation theory. So it's lambda times something, some other Hamiltonian, such that when lambda is very small and like really put the numbers on this. But then we were not able to take averages over only on this perturbation. So what we were able to do is to take average over the whole thing and show that whatever Hamiltonian that you pick, more or less behaves as the average. The average behavior.
Mhm.
So I mean, here still I don't have like a place where I can kind of increase my lack of precision or not. I mean, this here is still like step one, so to say.
Cool. Thank you.
Thank you.
Okay.
Thanks for a nice talk. I have a question about this GUE Hamiltonian,
Sure.
because you mentioned that it's like that you model finite resources, but GUE Hamiltonian is actually very complex. Like has like almost like maximal complexity as like evolution corresponding to GUE. So, but like physically, what we would expect, like for what class of Hamiltonians this would work, like for local Hamiltonians, because the dynamics is like totally, like we have work on that Jens also talked about it.
Sure.
It's totally different, right? So under what conditions you expect things to work?
Yeah, thank you for the question. And the answer is I don't know. So that's something else that we are willing to do, is having Hamiltonians which have it like correlation length, which is the case when going away from the diagonal elements. But then again, taking averages over these things, it's way harder, right? So the answer is that I don't know. So I was very happy to see Jens Eiser's talk, because there maybe also it's a way to do it, to take this not GUE ensemble, but taking one of his pseudo chaotic ensemble. But I start to read the article like on Monday, but okay, I'm still page 2, I guess. And I don't know if it's possible to take averages on this, and if it's easy or not. So it's really matter what we want to do and what we can do. Right?
Have you made some relation with that result from Gurianov? I think that shows the you know which result.
You mean like the ones like pure states do not exist, and like you would need infinite amount of energy to prepare a pure state, for instance.
Yeah, to make a projective measurement.
Yeah, or that, which is kind of related, right? Yeah, I think it's somehow the same spirit. Okay, so the sentence that I managed Jens Eiser to say, but I should say that I almost put in his mouth, was that Hamiltonians do not exist, right? So I mean to say like a sentence like real numbers do not exist and pure states do not exist, projective measurements do not exist. So what I think it's very related, but I was not able yet to make this connection kind of more formal, to say that given that to prepare a pure state you need infinite resources, then to learn Hamiltonian with infinite precision, these would also need infinite resources. So these are all things that would be nice to formalize.
Okay, it's really nice. Thank you.
Thank you.
Okay, I think we are up on time. So let's thank Fernando again. Okay.
At some point today, we are going to make a photo